And now we can have like our final presentation for this block one about forest management. So I would invite Dr. Yung Yang to present enhancing forest management with OpenET through forest health monitoring. Dr. Yung Yang received her MS and PhD in environmental science from the University of Massachusetts. She is an assistant professor in the Department of Forestry and at Mississippi State University. Her primary research interest is improving water resources sustainability and ecosystem resilience using field-scale evapotranspiration retrieved from satellite data. Her group is working on evapotranspiration simulation with multi-source satellite data from 3 meter to global to understand the impact of climate change and intensified human activities and to provide critical information for decision making and policy making. Welcome, Dr. Yoon.
Well, so I really appreciate that my presentation is right after Dr. Song and Jamie's presentation is because they just build this strong foundation of how important ET is for forest management, considering the water quantity and also considering the forest health monitoring. So my talk actually is trying to give you idea how we can use OpenET to help with these management issues. So first, when we talk about the forest health, there are currently, there are multiple ways to do it. For example, this is a forewarn system from your State Forest Service, which is using the NDVI, which is the vegetation index. So it shows you how green the vegetation is. If it's greener, it means it's healthier. But for a lot of times, when we think about forest health, when there's stress happened, not necessarily the first signal is the trees are going to change the color of the leaves or start to drop their leaves, right? So you may not see this NDVI change as the first signal of forest health condition change. So is there any other signal that can give us an early like a warning of the forest health issues? So here, of course, evapotranspiration. But the reason is because evapotranspiration naturally happens with the photosynthesis. So when there's the stomata on the leaves close, you will see the ET change. And the stomata, they close under stresses. So evapotranspiration could give us an earlier signal of forest health condition change, comparing with just to look at the leaf color change or leaf amount change. So how we estimate evapotranspiration? Well, for this workshop, this is not really an issue, right? OpenET can provide you the field scale evapotranspiration. But here I want to go a little bit to the theory part of how we really estimate ET in OpenET. Well, we all know in OpenET we have 6 different models, and a lot of these models they rely on the land surface temperature, which they use the energy balance method to estimate evapotranspiration. So here I'm using Alexi and Disalexi model as an example to show you how we use this energy balanced method to estimate evapotranspiration. This is also a model that I'm most familiar with. So here we can see that this model, it has 2 parts, Alexi and Disalexi. So Alexi part is a coarse resolution part. It combines the geostationary land surface temperature observation with a atmospheric boundary layer condition, so we can solve this energy balance issue at this coarse spatial resolution, and we can get the air temperature at the boundary layer, and then later we use that information combining with the finer resolution LST observation vegetation condition to run the Disalexi, which can disaggregate the Alexi ET from 4 kilometer to a finer spatial resolution. For example, when we use Landsat, we'll get a 30-meter ET estimation. So here is just to highlight a little bit about the theory behind the stage. But when we look at this thermal land surface temperature signal, I would say it's very similar as when we use a thermometer to measure our own body temperature. And it's also similar that your body temperature can tell you whether you feel well or not. It's the same for forest health. But here we are using this ET to look at the forest health and also at the same time look at the water quantity change. So I'm going to highlight a few of these ETs, the studies that we use ET for forest management. And these are the studies that I've been involved, or some of them I leading them. So first, let's start with just a small region, because when we first, without OpenET, when we just run this energy balanced ET method in our own server, we cannot really run over a large area at 30-meter spatial resolution. But we run kind of like a specific area that we are interested to look at the science question. So this is the first study that have been done for forest, I'll see, although it's a plantation. So it's Jamie's site. And this is a managed pine plantation. And I want to highlight this is because this is the first study that we applied the energy balanced method to estimate evapotranspiration at 30-meter spatial resolution and specifically look at the forest management. So this is one study that later I will actually highlight it with details. And then after this, I moved to this managed environment to a more natural forest. So this natural forest is in Missouri, and we all know in the 2012 drought, that drought didn't only impact the agriculture, it also impacted the forest. So we see a lot of the die out of the forest after the drought event. So my second study for the forest is on this site to look at how we can really use ET as a signal to find the forest health condition change, and whether we can use that health condition change information to help with the drought-induced mortality of the trees after the drought. So, and then I've been working with a PhD student from Rutgers University, and he's now a postdoc with USDA Forest Service. We look at the New Jersey forest, and we find ET is also a very good indicator for forest composition with different tree species, and also is a good indicator of different management. Here for management, we're talking about thinning, harvesting, prescribed fire, all these forest managements. So these are like small area studies, but really demonstrate the foundation of that. One, we can use the energy balance method to estimate forest ET. Two, we can use this ET as a signal to look at forest management and forest health change. And with OpenET, it really opened the window for us to look at regional applications. So one study I want to highlight here is also what Ge just talked about, look at the longleaf pine and loblolly pine species change caused possible hydrological change. And this is a work currently in review. And that data is I provided using the OpenET platform, but it ran the Alexi model. And another study that I also want to highlight for regional applications is over the Western states. Here are two studies. One is a ongoing work, which is looking at the disturbance impact for the hydrological processes over the entire Western U.S. for these camel watersheds, which are kind of like a controlled study watershed sites. And another one is a recent paper published on Nature Ecology and Evolution. It's using the OpenET data to look at the wildfire impact on the water balance shift. So this is a work collaborating with the EIS and NASA. So these are just a overview of what we can do, use the ET data to look at the forest applications. And later I'm going to highlight two studies. I just give you a detailed example how we really use them in these studies. So the first one is the plantation management one, and the second one is the drought-induced mortality one. So for the first one, is the one I always like to talk about in detail, is because it really demonstrates this capability of two-source energy balance method to estimate forest landscape evapotranspiration. So this is the Weyerhaeuser's plantation, and this is a site that in the North Carolina along the coastal area, which has a very shallow groundwater table. And we have two flex towers here, NC1 and NC2. On your right is our estimated annual evapotranspiration. So you can see with this 30-meter data, you can really see a lot of details of each of these plantation blocks. So these two flex towers, one is a mature one, which is NC2, and another one is a recent clear-cut and replanted young plantation site. So since this is the first study we look at the model performance for forest landscape, so we really did a very careful evaluation. We compared here the blue dots are observed ET data from the flex tower, and the red lines are our estimated data fused multi-satellite ET data at daily timescale and 30-meter spatial resolution. So you can see for both the young plantation and the mature plantation, we are doing a very nice job comparing with the field observations. And then with this data, we further look at the water use by stand age, which is also what Jimmy just mentioned. We all know that, from the single trees, you can measure how that tree is using water. But scales is hard. It's hard to push that point measurements to a regional understanding, right? So this is the first estimation from the remote sensing point to look at the tree water use by stand age. So we can see for this plantation area, when the x-axis is stand age, when the trees grow, this plantation, they tends to use more and more water, but around 15 and 20 years, that range, they kind of like the water use stopped at this high plateau and doesn't change that much. So this is just really straightforward to show you the regional water use by stand age. And here I highlight a few of these red points is because those are the drought year points. So we also see for this area, because it's the shallow groundwater, that drought didn't really impact much for the mature plantations. But for the very young plantations, you can see the stand age, they are very young plantations. You see a drop of water use during the drought year. It's just because they didn't get the time to establish their root to get to use the groundwater yet. So this is for stand age, but we want to look at time series to understand how these plantation changes over time. So with this, we want to compare the evapotranspiration, but I always like to see, even probably the tree didn't change much today and tomorrow, but today is sunny, tomorrow is rainy, you will have a very different evapotranspiration because it's just the naturally variation in evapotranspiration. So what we do here to remove that weather impact, to focus more on the vegetation and soil condition, is we normalize the ET with the reference ET. So we call it FRET. And then with this ratio, when you have multiple years ET data, and you can calculate multiple years ET, this FRET ratio. And for each day of 1 year, you can calculate an average FRET. So then we treat that average FRET as the baseline. So whenever you have a new data, for example, today's data, I can compare with this historical today's FRET. Then if that comparison is positive, it means, okay, so it happily using water. It demonstrates it is a healthy condition. But if it's lower than the normal condition, it gave us this warning, okay, it didn't really use the normal amount of water it should be. So that's a warning. So here in this figure, we use red and green. Red means a stress or disturbance condition, and green means a healthy condition. So with this and with our daily data, you can see on the bottom, we can really plot this FRET anomaly. So 0 is the baseline. So if it's above 0, means it's healthy. But if it's below 0, it means there's some kind of stress there. So with this daily curve, we can really find when the changes started, and also we can corresponding back to these different management. It turns out they either had thinning or harvest caused this quick drop of this FRET anomaly. And also along the years, you can see it gradually goes back from negative to above 0, which is a signal of recovery. So from this, we can also tell the recovery of this plantation after the disturbance. So to further look at the recovery, we actually plotted the monthly FRET anomaly from the time they get disturbed. So here is the x-axis is months after disturbance. And on the top is the FRET anomaly change, and on the bottom is the NDVI change. It's just for your reference. So you can see along these recovery trend, both of the FRET anomaly and NDVI, they give very similar trend, but you can see the NDVI one is more scattered, especially for the green dots, which are from the growing season. They kind of like get to this high plateau. It doesn't change much. So, but the FRET, the water use information, gave a lot tighter information here. So this is the first example, and I need to go quick for the second one because I know I'm taking a lot of time here. But the second one is we move to a natural forest. And this one, we have the mortality rate recorded. So that way we can compare the water use change during the drought year with the mortality after the drought year. So this is a site in central Missouri. Again, we did a very careful evaluation. It works well. So, and this is the FRET anomaly. So again, the red means stress and green means healthy condition. So you can see for the drought year 2012, we have a very severe stress over the entire region. It's because of the extreme drought event. And we can even actually quantify this. So this is the FRET, a cumulative FRET. So it's kind of like from the start of the season, we keep adding the FRET anomaly together. So if it goes negative, it means the stress is going worse and worse. And this is also highlighted by this red line, which come from this 2012 drought year. And we also linked this mortality with the drought year water use change quantitatively. So first, the first panel here is we compare the FRET anomaly with the drought year FRT anomaly with the next year's the mortality. So that's the first panel. And the second one, we get a better relationship when we use the mortality data with the previous 2 years information. It just gave us this information that, drought is not the only trigger for this forest more die out. A lot of the trees, they died after the drought is because they were not that healthy before drought already. So these are the two examples that I want to go through in detail to tell you how we use this. As the summary is really, ET is not just a water quantity. ET naturally linked with the forest health, is a effective indicator of forest health and management. So, and also I really want to see that OpenET with the cloud computing for large area, keep the 30-meter spatial resolution, really gave us unlocked a lot of potential for regional study. So with this, I'm going to conclude my talk. Thank you.
Thank you, Ian, for your great presentation. So we have time for questions. Yes.
Ian, thanks for the great presentation. So one of the questions that I thought was sort of outstanding in translating these mechanistic approaches to forests had to do with dealing with roughness. So with both terrain issues as well as canopy height changes across landscape scale spaces. Can you talk about how you're overcoming or addressing those challenges? Thanks.
Sure. Yeah. For well, the forest really have a very different structure comparing with the agriculture field. So actually, not just the roughness, it's also a lot of this under canopy circulations, and also how much the energy is stored in different parts. I think there are a lot of researches that we can further do to refine this part of study. But my experience working on this is for a lot of these closed canopy forest at the daily time scale. I feel the model is doing a very decent work comparing with our existing agriculture experience. But if it's relatively open canopy and very different structure, that might be something. And also, if you go from daily to hourly scale, that might be a issue. But I think that's the research part that really deserves a lot of more effort to carefully examine these. And I think I'm actually working with Devendra for a NASA eco-stress project, which we are looking at the energy participation and look at in the ET how to separate E and T for the forest. I think that study will also give us a lot of improved understanding for these questions.
Thank you. Have you had any experience looking at ET in the western forests, and specifically how OpenET works with different aspects and slope effects and shadows? that are created by hill slopes?
Well, I cannot really see this for the entire OpenET group, I think, because among our 6 different models, we are some part are different, and also how to treat the terrain effect and also the shadow effect is handled different in different models. But I think it's a very good point. There are something that I think E-metric is really handling the terrain effect very well. So generally, I think for the mountain area, there are I couldn't really see this for all the models, but I think John Walk, who did the careful, inter-comparison study, is the best person to answer your question. But it's a really good point.
Thanks. So this question is in regard to the application of OpenET. You gave 2 examples, again, in the Western US about large-scale disturbances and the potential for kind of these large area field-scale applications. The question is that with the intercomparison study results and kind of the inherent error that was coming out of the use of OpenET for forests, evergreen forests in particular, and the kind of the drivers of that error partly being the heat storage in forests or in the soil. How do you think that kind of the relative change approach to the use of OpenET pre and post disturbance is a viable option, given that if your disturbance is wildfire or large-scale mechanical thinning or clear cutting, the conditions pre and post that disturbance are very, very different and no longer necessarily resemble the evergreen forest that was the precondition?
Good question. Yeah, actually, this is something I think we really talked in detail in the Nature, Ecology, and Evolution paper, because that one specifically look at the wildfire impact for the western states. And the way we handle the differences is we, for each of these fire scars, we find a kind of like a reference site next to that scar as a pair study. But there, of course, there are a lot more details, to make sure how you can choose a perfect pair to study this wildfire impact. But back to the original question about whether OpenET has a larger bias for forest, evergreen forest. I actually still think the large bias we see from the intercomparison study, one is limited by the limited flex tower size we have in the study, and a lot of them they are in these complex like landscapes, and even hard for the flex towers to accurately capture the ET measurement. And also, I think for the heat storage, we cannot, before we really look into it, we cannot really just simply say, okay, so bias is caused by that. It's just possible. But I think we really, at what level that is the issue, caused this is something we need to further look at. And also for the, we are actually collecting a lot of evergreen forest sites from the southeast area, which we currently in this phase of intercomparison, we don't have that many flex towers in this region. But I think considering the large pine plantations in this region, collecting more data ground data for this region for the accuracy assessment will help us to better understand how really OpenET works for evergreen forest.
I have a question. So in your last example, you talked about the ratio between the ET and the reference ET, and then accumulating that over, many, many months. Did you also look at accumulating just the difference between the two instead of the ratio? I was just trying to like wrap my head around taking a ratio and then like adding it up over days as kind of like arbitrary units. And I'm sure they're similar, but I just wondered if you tried that and if it was better or worse, or as far as predicting mortality.
So you mean directly look at the ET? Or I may not understand it.
You had the ET divided by the reference
reference
ET
ET,
to get a
yes.
fraction, right?
Uh-huh.
You could also take
the
the
difference.
reference ET minus the ET. Just change the division sign to a subtraction sign.
We didn't try that. Well, I think one reason that we didn't try it probably comes from this magnitude difference, because if you do a ratio, it's generally from 0 to about 1, that value. But if you do a difference, you still need to find a way to somehow normalize it to a scale.
Okay, any final question? Okay, any other? Okay, let's go. Then we can finish.
Yeah, I was just curious, when you were doing the change detection with ET, if you had compared that to doing a similar change detection with NDVI. Because in the beginning you said that NDVI might not pick up those changes as quickly, and I was wondering if that was the case in your study.
Yep. Thank you for bringing up this question. Actually, this directly relates to my NASA EcoStress project, which we look at the water use change, and we also simultaneously look at the surface reflectance part of the change. So it's a study ongoing, but from the Missouri site, we did look at that site, which has this large die-out after drought. Based on that site, we see change in water use, but we didn't see change in NDVI. It's because even we consider it's a large die-out, but still it's not like what you think, a large area of forest is dying. It's still just, different trees in different area. It's hard to pick up from the NDVI actually, but that's based on just that site. Yep.
Okay, thank you so much for all the discussions. And we had great presentations today. And thank you so much, Dr. Yoon, Dr. Sun, and Jamie for the presentation. And thank you so much. I think if you want to ask more, so we can talk during lunch and after that. Thank you.